Torque is simply a rotational version of dynamics. This can be seen with how the equations for kinematics and dynamics are extremely similar to the ones for torque. The equations for torque include both kinematics and dynamics. For kinematics, we have omega f equals omega I plus alpha t, omega f squared plus omega I squared, plus 2 alpha theta. Theta equals omega initial t plus half 8 alpha t squared. And dynamics has torque equals Fr sine theta and torque equals I alpha. The symbols used include omega, which is angular frequency, alpha, which is angular acceleration, theta, which is the angle usually in radians, t, which is time, torque, which is tau, and F, which is force, R, which is radius, and I, which is moment of inertia. As mentioned earlier, torque is extremely similar to kinematics and dynamics equations, and as for kinematics, uses the same equations, just replacing the symbols. V, which is velocity, is replaced with omega, essentially the rotational velocity, and the same for the rest of the symbols, besides time, obviously, as time is always going to be the same no matter what it is, rotational kinematics, dynamics, whatever. Furthermore, you need to understand that the relationship between V and omega is that V equals omega times R, and R is just the radius of whatever object that is being used. Similarly, with kinematics, dynamics is also very similar to torque. The main equation for dynamics, F equals ma, is modified to be tau equals I times alpha, with I being the moment of inertia standing in for the mass, and A alpha standing in for the acceleration. This is important because torque is essentially just the rotational force instead of just a linear force. In dynamics, we discussed in 2 dimensions and 1 dimension how force works, but with rotational force, it's just a force with an angle, which gives us another equation, torque equals Fr sine theta. Here's a problem to practice rotational kinematics. A disk is spun from rest, uniformly accelerating to 50 radians a second after 10 seconds. What was its average acceleration? Because we have the final angular velocity, initial angular velocity, and time, we can use the equation omega f equals omega I plus alpha t. By plugging in the values, we come out to 50 equals 0 plus 10 times alpha, and you can further solve by dividing both sides by 10 to give you your answer of 5 radians a second squared. This brings us to our practice problem for rotational dynamics. Our practice problem will be saying that a solid disk of a mass of 10 kilograms and a radius of 0.5 meters is accelerating at 10 radians a second squared. What is the torque generated by the disk? The moment of inertia has different formulas throughout different shapes of objects. However, for a solid disk, such as this one, the moment of inertia will be equal to half of mr squared. By plugging in our values, we would get 1.25 as the moment of inertia of the disk. From there, we can just use the equation tau equals I times alpha to solve for the torque of the disk, giving us torque equals 1.25 times 10, which will be equal to 12.5 Newton meters. As always, thanks for watching, and I hope this helped.